I'll probably introduce Adel. He's going to be going through his presentation around profiling, clustering, internet-wide scans with FATT. Is it FATT or FATT? So I'll hand it over to Adel. If you want to make your way up, can we give him a very warm welcome? Thanks.
Hello everyone, and thanks for joining us today. I'm going to present my latest research about profiling and clustering internet-wide scans with a new tool I released a couple of days ago. So let's first introduce myself. I'm a lead security engineer at Salesforce in detection team, and also a member of the INET project for about 10 years now. Co-developer of hash profiling method, which is the profiling method for SSH. I'm going through that in a few minutes. And been working on a couple more open source projects you can find in my GitHub. So I'm going through some basics about the fingerprinting and different protocols. Then jumping into how I monitor internet-wide scans and how could we improve doing that, and then introduce my new tool FATT, and then the most interesting part of the talk, which is the observations. So these are the main questions I'm trying to answer through the presentation. So could we actually profile the attackers using the network metadata and fingerprints? Could we identify their tools and maybe discovering new connections, hidden connections which we couldn't find before, having network metadata and fingerprints, which is like a bit of more context? And possibly, maybe we can detect new evasion techniques as well. So I had these questions in my mind before starting doing this research, and now I'm going through some background stuff and then present the main research, and we will see the answers to these questions. So before we start, we need to know a bit more about fingerprinting techniques. There are lots of them with different use cases. For example, you all know about OS fingerprinting or TCP/IP stack fingerprinting, which, for example, you can do using Nmap or POF, passive OS fingerprinting. There are other types of fingerprinting as well. For example, browser fingerprinting. You can fingerprint the browsers and even the users itself by having a look at things and features like systems, fonts, languages, and stuff like that. But there are another type of fingerprints which is focused on identifying the clients and applications for different protocols, mainly cryptographic protocols like SSL, SSH, and RDP. For example, I guess you've heard about Geo Tree or Fingerprint, TLS, and hash. These are actually based on the fact that cryptographic protocols need to negotiate some parameters in clear text. So it doesn't matter which cryptographic protocol you use, SSH, RDP, TLS, they have to negotiate some parameters at first. So let's see how could we fingerprint the connections using these parameters we have in clear text. I'll start with TLS because my main focus in this research was on TLS, and then I expanded to RDP and other protocols as well. But we have a bit more details here about TLS. So for TLS, the interesting packet and message for us is the client hello. You can see here is a sample. It's actually a simplified version of message flow for TLS handshake. And the first packet you see here is client hello, which is important for us. We currently don't care about the rest of messages here, but basically how it works is clients send the algorithms like the cryptographic encryption algorithm, compression, and extensions it supports, and everything else using the client hello to server. Server responds back with server hello and selects one of these algorithms, and then the rest of negotiation happens, which is key exchange, certificate exchange, and stuff like that. This is the structure of client hello based on the RFC, which I linked under the page. So what you can see here is there is protocol version, a random string, session ID, cipher suites, compression methods, and extensions. But things which are interesting for us are these 4 fields. We don't care about the random string, we don't care about the session ID, because these are the things which can be changed during a session or depending on different clients and connections. So we can't really use those for fingerprinting. So the thing is, the cipher suite list and the cipher suite list we have in client hello message is actually in order of client's preference. So each client application may have different preferences and different combination of these with supported extensions, compression algorithm, and other parameters in the client hello can help us having some kind of fingerprints. So theoretically, we can have some unique fingerprints for applications, but when you look at it in real life, the thing is there are many applications using the same version of the same, for example, TLS library, OpenSSL or something like that, and as a result, they have the same geo tree. So you may see different applications with the same geo tree, which is fine. So a bit of history on this TLS fingerprinting thing. The first thing actually I found was a work by Ivan Ristic from SSL Labs, and it was actually an Apache module for just debugging purposes, which was logging the initial SSL handshakes and just focused on the cipher suites, nothing else. And it was extracting and logging that. So one of the use cases, as I said, was for debugging, but another use case was for cross-checking the supported cipher suites with HTTP client user agents. So the purpose was to find if there's any bot or scanner or tool trying to fake the user agents, and then if we check that using the supported cipher suites with a kind of fingerprint, we can actually detect that. So this was the main purpose of creating this mod SSL half. After that, I found the unofficial module for POF, which you can see here is a sample of the fingerprints they have. It's a bit ugly, but better than the previous one, because it's not just based on the cipher suites, it includes other parameters in the client hello as well. But this is just an unofficial one, which isn't merged with the main POF code base. The next major thing was in 2015, done by Lee Brotherstone, which he created a couple scripts and tools for matching, creating, and exporting of TLS fingerprints. You can see here is the composition he used for creating his own fingerprint, which includes different things, not just the cipher suite. It includes the TLS version and compression and elliptic curve as well. So the thing is, he actually uses a binary format for the database, and what you can see here is the export of that database into JSON format. It's really good, better than the previous works, but again, it's a bit hard to share these fingerprints with the community and have some kind of detections based on that. So that's why three of our guys from our team in Salesforce started working on Geo Tree, which is currently the most common SSL fingerprinting method. The composition of the parameters we used for fingerprint is almost the same as the fingerprint TLS. And the thing is, we put all these things together and hash it with MD5. So it's easier to share and implement it on different devices and tools. And currently, many tools in the community started adopting these, like Suricata, Bro IDS, and many other tools, even PacketBeat, and many different tools out there started supporting this. So let's move on to the next protocol, SSH, and then we go back to TLS again. So for SSH, we actually have a message called SSH message KEX init, which is a key exchange initiation. And as you can see here in the screenshot, there are some fields like algorithms, key exchange algorithms, encryption, MAC, compression, and language, which potentially can be used for fingerprinting. We actually started working on this several months ago. It was late 2018. Ben Reden and me started working on this and had an initial composition, tested on that on our honeypots and different scenarios, and removed some parameters from the final composition because they were a bit dynamic. We couldn't use those for fingerprinting. And then the final composition is what you can see here: key exchange algorithm, encryption algorithms, MAC, and compression. We put all these things together and hash it in MD5, almost the same way as we do it in Geo Tree for TLS. And then we have hash for client SSH applications and hash server for SSH servers. Just another point here. Before this KEX init message, you can see there is another negotiation called server identification string and client identification string. This is actually something which you can easily change, but by default, if you have a look at like the OpenSSH clients or servers, they have a specific string here. For example, you can see here, let me use the magnifier. So this is, for example, for a specific version of SSH on Ubuntu. And you can easily change these. For example, if you have used the Nmap, the SSH scanning module in Nmap, you can easily change that. But most of the times, no one changed that. But I will show you, even if someone trying to change that, we can still detect what the actual client or server was. So here are a couple examples and use cases of this SSH fingerprinting technique. You can see the first one is ncrack. So in ncrack, you can customize the SSH identification string that I told you just right now. But it doesn't matter if you change it to OpenSSH or anything else. You always have this specific hash because of the order of encryption algorithms and everything in ncrack library. Another interesting thing which I found several months ago was that Cobalt Strike also has a SSH client built in, and there's no way you can change that built-in SSH client. So I had a look at that, and apparently it has a specific SSH fingerprint. So if you search for this SSH fingerprint inside your network from Windows systems to Linux systems, that's like certainly something like Cobalt Strike. I actually tested that, and it actually doesn't have any false positive. And then the last one here in the examples is the Cowrie honeypot. So you know that in honeypots we try to fake a specific protocol or server or something, and here in Cowrie, which is a SSH honeypot, you can customize that string which tells the attacker, for example, I'm OpenSSH or something. But if you have a look at the hash, it actually uses a static list of encryption algorithms and compression and cakes, all those stuff. And that actually results in a unique hash. If you start searching this in Census or Shodan, you can find many SSH honeypots out there, and it's kind of interesting. And the last thing about the SSH fingerprinting thing here is a simple tool I created called HashGen, because the problem with TLS was for Geo Tree. I know many people and companies out there was looking for a database of Geo Tree fingerprints to use for detection or baselining, but it's a bit hard to automate creating that. So I created this HashGen. Actually, there is another version for Geo Tree as well, which I haven't released yet. I'll probably do it soon. So what HashGen does is, it's actually a simple Python script and also a Docker file, which will be modified by the Python script dynamically. So it starts changing the Docker file and using different operating systems with different OpenSSL versions, and then tries to initiate a connection and captures the hash value. So here you can automate the creation of this database for yourself. Okay, let's move on to another interesting protocol here, which is RDP. There's been a lot of discussions around it during the past couple of days, so I thought why not including that in this presentation. So I've been working on capturing the RDP traffic on my honeypots from several months ago, but started looking at that more closely from a couple of days ago. So let's see how we can actually fingerprint the RDP connections. Before we start doing that, we need to learn more about the RDP itself. We need to know how RDP works, and is it using TLS or is it like using something else? So it actually uses TLS and also another protocol, which is the RDP's standard security protocol. So I will show you in the next couple of slides how we can fingerprint the RDP connections. So the first RDP connection we have is the negotiation request. It doesn't matter if you use TLS or standard RDP security protocol, you always have this negotiation request, and in the negotiation request there is a requested protocols field. And here you can see that the protocols here is set by the client. What we have here in the screenshot is TLS, CredSSP, and EUA. So client actually tells the server that I support these protocols. Then the server selects one and continues the connection. So the thing is, if the client and server uses the enhanced RDP security, which can be TLS 1.0, 1.1, 1.2, CredSSP, or RDS TLS, they actually use TLS, and that's good. So we can still fingerprint these connections using Geo Tree. But if it uses the standard RDP security, it's actually even better, because then we have other list of parameters we can use for fingerprinting. So I will show you here an experimental fingerprint method I created for standard RDP security. Again, I say this is not perfect. It's just for my use case. I will probably work on completing that and finalizing that in the coming weeks. But the current composition is major version, minor version, cluster flags, encryption methods, ext encryption methods, and channel depth. So the thing is, here you can see in the screenshot that if we use RDP standard security, we have another message, which is client data. So after that initial negotiation, we have the client data. And in client data, we have many interesting fields, which shows what RDP client is used for this connection. So I will go back to that in the observation section of this presentation. But now let's have a look at other protocols and see if we can start the fingerprinting those as well. So for HTTP, actually, there is a great work by NetSquare guys back in 2003. This is actually for fingerprinting HTTP servers, but the same approach can be applied to HTTP clients as well. There are several things you can use, but the most interesting one is the order of HTTP headers. So this is something for HTTP. Then the recent work I started doing is on Quick protocol, which actually has two main versions, Google Quick and IETF version. So recently I started creating a Go-based library for Quick for extracting the Quick client hellos. And you can see here is a sample screenshot of that. I'm continuing working on that to support IETF version as well. But what other protocols can be fingerprinted this way? Basically, any cryptographic protocols having a clear text negotiation, and even non-cryptographic protocols like HTTP, as I told you, the order of headers or some other features can be used for fingerprinting. So why we should do that? How these fingerprinting and metadata can help us identifying the attackers' tools and profiling them. So the problem is the current honeypot has limited network logging, and they usually log just general network information and some application level data. Like, for example, in carry, you have SSH commands, you have some authentication related logs and stuff like that. The same thing for RDP honeypots and other honeypots out there. But there are no network metadata and handshake logging. So, and actually that's the reason why all the research we see, almost all the research we see out there about the honeypots, they're mostly about like the number of connections to different ports and the scanning trends and stuff like that, but nothing interesting other than that. So my main question was, if we log handshakes and network metadata, could we find anything else, some other interesting stuff which I told you at the beginning of my presentation? So let's have a look at what are our options for logging the network metadata. So Bro or Zeek is one of the best things we can use for that. It's actually a pretty mature tool, and it's really flexible. But the problem with Bro is if you want to add a new protocol, like for example Quick, or if you want to extract new fields from RDP, it's a bit hard. Like, I won't do that. Another one is Suricata. So Suricata is a bit easier for expanding and adding new protocols, but currently supports HTTP, DNS, and TLS. It's good for collecting network metadata in production, but it doesn't work for my use case. And then there's T-Shark, which is actually what I used, because maybe it's a bit weird, because like T-Shark isn't good for like collecting network logs in production, but it actually works for my use case. I will show you. And then there's another tool which is released recently, which is based on Go. And it's actually pretty good. I haven't tested it, but it's one of the best tools out there, which is Netcap. So this is actually the first version of my research, which I presented last year in the HoneyNet project. It was mainly focused on TLS. So what I used there for monitoring was Bro and Geo-Tree script. And for the honeypot, I just used an Nginx, nothing special, just an Nginx with some open TLS ports. And then I joined that Nginx logs with Bro logs and like created this dashboard and some context around the connections I was seeing. So this year I changed that a bit. Instead of Bro, I started using my own tool, which released a couple days ago, called FATT, Fingerprinting All the Things. So it's actually based on T-Shark. It uses the Python's wrapper for T-Shark. And the reason I actually used that was because I wanted to log different new protocols like Quick, RDP, and I wanted to have a way to quickly create an experimental fingerprinting, the same thing as I showed you for RDP, RDFP. So this was, I guess, the best choice for that. And for the honeypot part, I used, again, Nginx for TLS and HTTP ports, RDPy for RDP, and Caddy, which is a web server for Quick. So then I collected the logs using FluentD, MongoDB, and Metabase. It doesn't matter what you use. This is just what I wanted to share. So let's have a look at this new tool and see how we can use that for our research. So this is actually, if you want to, this is the link you can use, and if you scan this QR code, you go to the GitHub page. As I told you, it's a PyShark-based script for extracting network metadata and fingerprints for, currently it just supports TLS, SSH, RDP, HTTP, and gQuick. I'm adding an IETF version of Quick, MySQL, MS SQL as well. So my main use case was for monitoring honeypots and network forensic, but yeah, it's up to you. You can use it for different things. Easy to add new protocols. The JSON output is good. You can just import it into your Splunk or any other tools you use for log management and analysis. And maybe the only downside is the performance, because it's based on T-Shark, so it's not really like high performance. And that's the reason I started creating a version in Go using the Go packet as well. So that's still under development. So here's a sample log from FATT, and as you can see here, this is listening the network connections in live mode, and just prints some a summarized version of the connections, and also log that into a JSON file. So now the most interesting, at least I think it's the most interesting part of the talk, which is the observations. Now let's see what we can understand about the attackers and tools using these metadata and the fingerprints. So this is just a simple diagram you can see here. The interesting thing here is that you can see an actor started scanning some TLS ports like 992, 443, and other ports. And the interesting thing here is he or she actually scanned all these ports 54 times. Like you can see, the graph is really cool, and it shows that a specific actor. But this is a simple thing you can see in other honeypot research as well. But let's see what other things we can have. So I started visualizing the logs, and I used IP source as the as one node and Geo tree as the other, and connected these two together. So this is what I saw. I didn't really expect to see this. So if you look closer, let me zoom into that. So here you can see some interesting stuff. Like this is something we actually expect to see. Different IPs connecting to one specific Geo tree. That's normal because they use the same tool like Google Chrome or Nmap or something. And this is kind of normal things we should see. But have a look at this. Or this one here. Or this one. So these are the normal things I showed you. I'll skip that and go to the interesting one. So what you see here is that there are like 10 IP addresses with more than 500 different Geo trees. This is a bit weird. I actually selected one of the IPs, and you can see just one of these IPs has about 500 Geo tree values. So let's look at it a bit closer and see what's the reason for that. So this is actually an attempt to avoid SSL fingerprinting by randomizing client hello fields. I first actually identified this at late 2017 and reported in July 2018 last year in the Honeynet project. But recently, some researchers from Akame also started observing these and reported that actually several days ago. And yeah, this is just a pointer to that, just for record. So let's have a look at that. So here's one of the Tls fingerprinting evasion attempts. You can see here the Geo tree field is a bit weird. It's too short. This is the same, like, let me, so can you see here the Geo trees? Geo trees are the same, IP sources are different, and Geo tree fields are a bit weird. You can see that here again. So if you look closer, you see that these numbers are changing. Actually, if you sort that, you can see that it starts from 1 going to 2, 3, 4, 5, and increases. This is another one, which you can see here. There's an IP source, again, with lots of Geo trees. And again, when we look closer, here is actually a more interesting pattern. Can you see the pattern here? This is another one from the same actor. So if you have a look at this pattern, like these numbers I highlighted will be removed in the next packet. Like have a look at this one, 61 will be removed in the next one. 53 will be removed in the next one. 156 and 60 from the next one. So the pattern is like so obvious when you have a look at that Geo tree fields. These are two other samples here which you can see, again, from the same actor. So this one is actually my favorite one. It's actually kind of interesting. You can see 4 different clusters here, and they're all connected together with some links here. So the IPs are completely different, Geo tree is different, but because of these nodes here, we can connect these 4 clusters together, which is interesting. So the pattern in this one is even more interesting than the previous one. So here you can see the green box. There's something, then something else, then again the first one repeated 5 or 6 times, and then in a small one, which is actually an invalid cipher, and then a wall of text. So this actually happens every time for the same actor I've observed. And the interesting thing is, when you have a look at these values, it's actually different every time, but the pattern is the same. Like, have a look at the next one. The values are completely different this time, but the pattern is the same. Something, then something else, then the first thing happened 5 or 6 times, then that invalid thing, and then the wall of text. So it's actually interesting. We can identify that actor always using this pattern. Just a few other things, and then I'll show you something on RDP. So for profiling the tools and actors, you can see here, because of some links between these graphs, you can profile the tools and actors actually. You can understand that this is the same actor using the same tools, because, for example, in this example here, you see like the IPs are different, but just because of this geometry here, we can connect these two IPs together. There's also a Tor exit node monitoring as well, which you can see these IPs here are completely different, but the geometries here can connect these IPs together, which means that this is the same actor using the same tool. Let's have a look at some observations on RDP. So in RDP, I've started seeing these connections which shows some randomized cookie string. Another interesting thing here is the requested protocols is empty, which isn't a normal thing. And then here the fingerprint, which I told you is an experimental fingerprint, shows that all these random cookie strings has 4 specific fingerprints each time. And this is because the actor started changing the encryption algorithm is used. This is another one which you can see. You actually can't see the source IPs, but the source IPs are different. RDFP or fingerprint is the same. And here the cookie is like something like a brute force. And the last thing in the RDP is the geometry of RDP scanners. So the previous thing I showed you was actually the scanners using the standard RDP security protocol. But this is the ones which are using the TLS, and this is the geometry of those things. I wish I had like more time to go through these. There was lots of diagrams and stuff to show you, but I will finish that with another observation from SSH. The same thing happens here in SSH as well. You can see here there are different client strings which is randomized, but all has the same hash value, which is the hash value of Golang SSH library, which is actually for a malware using Go. This is actually just the only current thing that I see in Quick, which is just one actor scanning my Quick honeypot every day with this user agent, which isn't a valid user agent for Google Chrome. I probably provide more details and graphs, and I'm also going to release the data set if you're interested soon after the talk. But just to conclude the talk, you saw that with capturing network metadata and fingerprints, we can identify different actors and tools and profile them, discover new connections between the actors which we couldn't find before using metadata and fingerprint, and finally detecting evasion techniques that you saw in the talk. So I guess I don't have enough time anymore. If you have any questions.
That was absolutely fantastic. I love listening to people speak that are highly passionate about what they do, and that's a really, really good tool. We're just talking about it before, and he says, I can talk about this for hours. So if you do have any questions, please meet him outside. But let's thank Adel.